Hi, everyone. In this video, I'm going to go through the study guide for Unit 8. This is for the Chem 1-2 stoichiometry quiz coming up. So this problem has the study guide has 3 stoic questions. These are the type of stoichiometry problems you'll be able to answer. You might also get some questions about the nail lab, other things your class may have focused on, so make sure you pay attention to that as well. But this video is just going to cover stoichiometry. Okay, so let's start with this one. We have 61.2 grams of gas are released when rubidium oxide breaks down. What mass of the original sample must have decomposed? All right, so we're going to start with the balanced equation. So we have rubidium oxide breaking down. So that's going to be Rb2O turns into, it's going to split into its 2 elements, Rb solid plus O2 gas. Balance it out. Looks like we need 2 there and a 4 there, giving us a 2 to 4 to 1 mole ratio. All right, so the problem says if this many grams of gas are released, that must be this one. It's the only gas. So let's turn 61.2 grams of O2 into moles. Remember, oxygen is 16.00, but oxygen gas, O2, is 32.00. Oh, times 1 mole over 32.00 grams. It's a molar mass of 2 oxygens. 61.2 over 32 gives us 1.91 moles of O2. So I'm going to put that right under my O2, 1.91 moles. And what are we looking for here? What mass of the original sample must have decomposed? So my X goes right here. All right, let's apply the mole to mole ratio. We have a 1 to 2. So what am I going to do to this number? I'm going to double it. So 1.91 times 2 gives me 3.82 moles of Rb2O. So that's what must have decomposed. We're looking for mass, so we're just going to convert this into grams. All right, so rubidium 85.47. That's 1 Rb. Oh, no, times 2 Rbs. Plus 1 oxygen gives me 186.94 grams per mole. Mole cancels mole, 3.82. 714 grams. Now you might be saying, hold on a sec, how can 714 grams turn into just 61 grams of gas? Well, you got to figure a lot of that other mass becomes rubidium. And in fact, if I do a real quick check here, just to be extra thorough, not that you would ever need to do this, let's just see if mass is truly conserved. So if we had 3.82 moles of rubidium oxide, we're going to double that. 3.82 times 2 gives us 7.64 moles of rubidium get formed. Multiply that by rubidium's molar mass of 85.47, and I get 653 grams. That's how many grams of rubidium form. Add that on to my 61.2 grams of gas, and lo and behold, 714 grams. So it all works out. Question 2. Solutions containing. So I know right off the bat, it's going to be double replacement. So aluminum chloride, AlCl3 aqueous, plus potassium oxide, K2O aqueous. Again, I know these are aqueous because I say solutions of, meaning they're both solutions. I'm going to form aluminum oxide, Al2O3 solid. I'm going to form potassium chloride, KCl aqueous. Now, how do I know these two? I've just done these enough that I can recognize what's solid and aqueous, but what would you do is check your solubility table. So you would find aluminum oxide, let me just confirm, aluminum oxide is solid and potassium chloride is aqueous. All right, this gives us a 2 to 3 to 1 to 6 ratio, 2, 3, 1, 6. Okay. So we have 3.98 grams of aluminum chloride and 4.05 grams of potassium oxide. So notice it gives us the grams of both of our reactants. That means this will be a limiting reactant problem. You can't just pick whichever reactant you want. You have to identify the limiting one and go from that. So 3.98 grams of AlCl3 times 1 mole over the molar mass of AlCl3 to 26.98 plus 3 times 35.45. Oops. 26.98 plus 3 times 35.45 gives me 133.33 grams. 3.98 grams over that gives me 0.0299 moles of AlCl3, 0.0299. Potassium oxide, 4.05 grams of K2O. Let's get the molar mass of K2O. So 39.10 times 2, that's 2 Ks, plus 16 is 94.20 times 1 mole over 94.20 grams. 4.05 over that gives me 0.0430 moles of KCl. 0.0430. Okay. We need to identify the limiting reactant. And this actually looks too close to call for me, just visually. It's a 2 to 3 ratio. So the way I do this is I'm going to need 1.5 times more of this compared to that. So let's see if I have it. 0.0299 times 1.5 gives me 0.0449. Do I have that? No, I don't. That means that's the LR. Here's the other way of solving for limiting reactant. Moles divided by coefficient equals, moles divided by coefficient equals, smaller numbers are your LR. Let's just confirm. 0.0299 over 2 gives me 0.0150. 0.0430 over 3 gives me 0.0143. Which one's smaller? The one on the right. So these numbers can go away and we have our LR. All right, what are we looking for? First, we're looking for the mass of the precipitate that will form. Okay, mass of precipitate. So my X is going to go right here. That's precipitate. And which one do we base it off of? The 2 or the 3? Well, we have to base it off the limiting reactant. So I have to go like that. You can't base it off the excess because that's not the correct amount that's going to react. All right, so what do we do to that number? Well, I'm going to divide it by 3, which gives me 0.0430 over 3. 0.0143 moles of Al2O3. Let's turn that into grams. So 2 Als plus 3 Os, 101.96, which gives me a final mass of 1.46 grams. 1.46 grams. All right. Number 2 here. Now what I'm going to do is I'm going to flip this. I'm going to clone this page because I want to keep the numbers available. Just find my mouse. All right, let's clone this and switch back to tablet mode. All right, I'm going to clear up some space here. Okay, for this one, I'm looking to figure out how many grams of excess remain unreacted. So for this, I would make a BCA table. If your teacher's gone through that with you, that's where we make a B for before, C for change, and A for after. Now, even if your teacher hasn't used the phrase BCA, they've probably arranged these in a way where you're starting with the original moles, I call that before, taking away the moles that react, change, and seeing how much you have left over after. Now, we don't need to fill in a full BCA table for this part. I'm really just looking for it for this. Although maybe if this were a test or quiz, I would maybe just do a BCA table because that would help with number 1 and number 2. All right, so what's going to happen here? My LR is going to be completely depleted, minus 0.0430, leaving me with nothing. And how much of this is going to react? Not all of it, right? Because it's the excess. How do I figure it out? Well, I'm going to apply a 3-to-2 ratio from here to here. Because notice, for every 3 moles of the LR that react, 2 moles of the ER are going to react. So how do I apply a 3-to-2 ratio? Well, what I would do is divide it by 1.5. You can also multiply by 2 moles over 3 moles, which is the same thing. You can divide by 3 and divide by, yeah, that would work. Divide by 3, multiply by 2. There's several ways of doing this. You can even put an x here and cross multiply, just ignoring the 0.0299, where the setup would be 2 over x equals 3 over 0.0430. All right, well, I'm just going to go divide it by 1.5. So 0.0430 divided by 1.5 gives me 0.0287. X equals 0.0287. Now, is that being formed or taken away? Well, it's being taken away. It's being reacted. So we're going to say minus that much, leaving me with, looks like I could do this one by hand, 0.0012. Okay. Now, you might say, ooh, 3 sig figs, 3 sig figs. Let me stick a 0 here to get 3 sig figs. Nope. When we subtract, we don't do sig figs. We do decimal places. So 4 decimal places, 4 decimal places, 4 decimal places is correct, which ends up losing a sig fig, but that's how it is. Okay. This is moles of excess that remain unreacted. We now just need to turn that into grams by multiplying. So 0.0012 moles of AlCl3 times the molar mass, which I remember from before is 133.33 grams per mole, gives us 0.159996. I'm going to call this 0.16 grams, and I'm purposely doing 2 sig figs for that. Even though the problem said 3, the amount of moles left unreacted had 2 sig figs. So I do 2 sig figs times that, 2 sig figs. Okay. And let's do our final part. I'm going to once again clone this page so I can keep this nice and orderly. All right, let me erase some of this. All right, if I'm going to do a sketch, all I really need is my balanced equation and my LR identified. Okay, so to sketch this, I'm going to go beaker number 1 plus beaker number 2 yields beaker number 3. I'm going to add water to all 3 beakers. In my first beaker, I have aluminum ions, Al3 plus, and chloride ions, Cl minus, with waters facing towards the aluminum and away from the chloride. Second beaker, I have potassium ions, K plus, and oxide ions, O2 minus, with waters facing towards the potassium and away from the oxide. Notice, even though oxygen is a diatomic, a Brinkelhoff, same with chlorine, when they're split into ions, they do not pair up. Final beaker, I have Al2O3 at the bottom. Al2O3, that's solid, that settles out on the bottom as my precipitate. I have K plus and Cl minus ions floating around with waters pointing towards that and away from that. But we're not done yet. Because it's an LR-ER problem, I have to put my excess reactant in the final beaker here, in the solution. We call this the supernatant, is the liquid above the solution. It's the water that contains the ions. So my excess reactant was aluminum chloride. Now I'm already going to have one of these. Which one do I have? Chloride. So the third ion that I need to add is going to be aluminum, Al3 plus. These are the excess aluminum ions that were left over from my excess reactant. So you notice that my supernatant here, my solution, contains 3 ions, potassium, chloride, and aluminum. The only thing missing is oxide. And if you could actually add some oxide ions here, you would notice that those would react with the excess aluminum ions to give you more precipitate. Okay, let's move on to the last problem. We have ethanol combusting in the presence of 109 grams of oxygen gas. All right, let's balance. C2H5OH. I didn't tell you the state of matter. I know from experience this one is liquid. In fact, I'll probably add that onto the study guide after this. Plus O2 gas yields CO2 gas plus H2O gas. All right. Now you might be saying, why is it H5OH? Why can't you merge them? Well, for the purpose of balancing, you're welcome to do that. And by the way, this OH is not hydroxide. This is, it gets a little bit into organic chemistry, but the fact that this molecule has an O bonded to an H at the end is very important to its structure. So it's often written that way. Now, for the purpose of balancing, if you want to make it C2H6O, you can do so. I should be able to leave it like that. All right, I like to do my H's first. So I have 6 here and 2 here. So I'm thinking 3. Now, in combustion reactions, my gut instinct is usually to never put an odd number in front of my water, because that'll give me an odd number of O's, which I can't have. But this time's different because my hydrocarbon fuel has an oxygen in it. Notice that gives me an odd oxygen. So let's try it. Let's put the 3 there and see if it works out. H's are good. Carbons, 2 carbons are good. Now let's add up our oxygens and see what we need. 2 O2s is 4, 3 O's is 3, 4 and 3 gives us 7. So we need 7 oxygens on the left side. Well, I have 1 here and 2 there, so I need 4 more essentially. I mean, I need to get to 7 is where my logic is. Now, I could put numbers in front of this to get myself up to 7, but I don't want to do that because that's going to mess up my C's and H's. Let's leave this as a 1 and think how many more I need. Well, I need 7. By leaving that as a 1, I need 6 more. So if I put a 3 there, I'm good. 7 oxygens, 2 carbons, 6 hydrogens, 6 hydrogens, giving us a 1, 3, 2, 3 mole ratio. Okay. So I'm going to be making a BCA table. I kind of want to keep this organized here. Let me do my molar mass conversions really small, like down here. Okay, so I can do it down here. 32.9 grams of ethanol times 1 mole over, let's see, I got to add this up. So 12.01 times 2 plus 6 hydrogens is going to be 6.06 plus 1 oxygen is 16 is 46.08. 0.08 grams. 32.9 over that gives me 0.714 moles. 0.714. Oxygen, I have 109 grams of O2 times 1 mole over 32.00 grams. Remember, I know oxygen says 16 on the periodic table, but this is O2, not O. And that gives me 3.41 moles of O2. 3.41. Okay, so we're looking to make a B, C, A table. The B is before, C is change, A is after. Now, before the reaction, we have this many moles of that reactant, this many moles of that reactant. How many moles of these products do we have? Nothing, because the reaction hasn't started yet, so I fill in zeros. Next thing we need to do is identify the LR and then deplete that LR. Now, I can look at this right now and identify the LR quickly. And that's where you kind of want to get. You want to be comfortable and quick enough with these that you can notice that. So I'm noticing that it's a 1-to-3 ratio. And I can tell just by looking at these numbers that this one is more than 3 times, right? Because if that were 1, you would have a 3 here. Well, it's less than 1 and we have more than 3. So I'm going to identify this as my LR. And that is my ER. Okay, the LR gets fully depleted, leaving us with 0. How much of my excess reactant is going to react? Again, not all of it. It's going to be 3 times this much, right? Because it's a 1-to-3 ratio. So if 0.714 moles of my fuel react, I triple that. 0.714 times 3 gives me 2.14 reacting. So minus 2.14 moles, which leaves us with 1.27 moles. Now, all these numbers I'm writing in the table are moles. Okay, how much CO2 is going to form? Well, which one do I base it off of? The 1 or the 3? I base it off the LR. So if it's a 1-to-2 ratio, so if that many moles react, I'm going to form twice as many moles. So 0.714 times 2 is 1.43, and that's going to form on this side, giving me 1.43 moles. And for the water, I can just multiply that answer by 1.5, giving us 2.14 moles. 2.14. I could have also noticed that if that's how much reacts here, that's how much going to form here. Okay, so the BCA table is done. BCA table doesn't require grams. It's just moles of everything. And it's just a nice tool to organize a complete problem like this. How many grams of the excess reactant remains unreacted? Well, we already worked out the moles, right? 1.27. So if 1.27 moles, let's multiply that by the molar mass of oxygen, which is 32.00, and that's going to give us 40.6. That's how many grams remains unreacted, 40.6 grams of O2. And finally, if 25.4 grams of water were collected, what's the percent yield? And a lot of times people say, well, percent yield of what? Well, since we're collecting the water, it must be the percent yield of water. So how many moles of water form? 2.14. If we multiply that by the molar mass of water, 18.02, that'll give us the theoretical yield of water. How much water is supposed to form when these reactants go into the reaction? 2.14 times 18.02 gives us 38.6. 38.6 grams of water, I'm going to say should form. That's my theoretical yield. So final setup for percent yield is going to be 25.4 grams, which is given to us in the problem as our experimental yield, divided by 38.6 grams, which is our theoretical yield. Maybe I said that wrong before. The experimental yield is one given in the problem. The theoretical yield is one you calculate. And that'll give us our percent yield times 100%, of course. 25.4 over 38.6 is 0.658 or 65.8%. Okay, and I got it all to fit on one page. Very nice. All right, good luck with your stoichiometry quiz.